Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, physics perspective. This is lecture number 7 and the topic of of this lecture is MOS capacitors part 2. What we will be doing is we will be quickly going through the CV characteristics. We will go through the ideal CV characteristics. Then we will take up a MOS capacitance and see how does the CV curve behave under moderate frequency, high frequency and low frequency, and what is the physics behind that. And then we will be finally looking into the CV characteristics of trap charges. In my previous lecture, I had already dealt a part of this CV characteristics. Just to give you a further insight into it, why this is important is that in all considerations when you do a circuit analysis, it's very important to appreciate that what amount of capacitance a device will be giving when you apply a particular bias, right. That is the motivation for this lecture, that at the end of this lecture you can actually predict the amount of capacitance a device will be giving when you have a certain bias being applied to the device, right. And therefore your RC time constants will be also defined by such type of study. So, I have already told you earlier the capacitance of the device is given by dq dv, which is shown here. Let me reshare it and consolidate your memory. It is basically dq dv. What is dq dv? dq dv is primarily the differential change in the charge to the differential change in the voltage. So, very simple and very straightforward. So, if I have a capacitor here and if I give a voltage here, and this voltage is basically a differential voltage, right, because of which I had initially a capacitance C0, I had a charge which was Q0, now it becomes Q0 plus delta Q, then we define delta Q times divided by delta V to be equals to capacitance, right. So, this is a simple parallel plate capacitor which we have defined in this case, right, and it has nothing to do with other cases, and we will just look into this capacitance of the device. In reality, how do you do it is something like this, that if you have a device which is a MOS device specifically we will be looking into rather than a parallel plate capacitor, then in a MOS device you apply a DC bias which is given in point number 4, and then superimpose on that you will have an AC signal, right. So, your DC bias will be responsible for biasing the device either at saturation or at inversion or at subthreshold, and when they apply AC signal, the bias will move in the sinusoidal fashion if it's an input AC signal, and from there you can predict the value. So, it will look something like this. The AC signal will be a small signal AC which will be going like this, it will be a small one, and this will be superimposed over a DC cycle. So, I have a DC input and over that you have AC. Now, since it is an AC, you need to therefore understand at each and every voltage point how should the device behave. That was the reason why we always say that the AC signal is applied over a DC gate voltage. As I discussed with you earlier, that we are assuming that initially there are 0 charges trapped in the oxide layer and there are no trap charges in the interface layer between the oxide and the semiconductor, right. That is the first point which is mentioned here. And there are 3 operating conditions which we will be looking into, which is accumulation, depletion and inversion. These 3 basic modes of operation we will be looking into as far as MOS device is concerned. Let us come to the first one, like accumulation CV, which I have already dealt in the previous lecture, just to solidify your memory. Let us look at this point. So, I say capacitance per unit, when I say C prime, I mean to say capacitance per unit area. So, capacitance divided by area is basically my C prime, right. And what happens in accumulation is that you apply a negative bias on the metal side. Let us suppose I have a p-type substrate here, right. I have a p-type substrate. You apply a negative bias on the metal side. When you apply a negative bias, what happens is you will have negative charges being accumulated on the metal side. So, that is what I was showing here. You see that minus q of q bar, which is charge per unit area. Since it is a minus sign on this side, obviously to counteract the minus sign, there will be a positive Q sign on the semiconductor side, correct. So I have a negative Q on the metal side and a positive charge on the semiconductor side. Now if you apply an AC signal such that there is an excess charge of dq prime on the metal side, then this will correspond to a dq prime charge on the semiconductor side, and it will be positive in nature. Why? Because you have applied a negative voltage on the metal side. So the electric field will be towards this direction, right, and all the holes therefore which were here will be all pushed towards this side, right, and there will be accumulation region. And we define the accumulation therefore is nothing but like a simple capacitor, your parallel plate capacitor. So it's a parallel plate epsilon ox divided by tox into a, sorry, you get into a here, right, and therefore when you write as a per unit area, you divide this by a, this cancels with this and you are left with epsilon oxide into tox, right. Let's come to the depletion capacitance now. Now the total capacitance is basically a series combination of the oxide capacitance and the depletion capacitance. What is the origin of a depletion capacitance? Let me give you an example. I give a positive charge, again the same concept. I have a p type semiconductor here, I have a p type semiconductor, I have a metal here, right, I have a metal here, I have an oxide here, right. Now in this metal I apply a positive bias which is not very high to invert the channel, but at least so much large that there is a small positive charge formation on the metal side. This will do what? Will create a depletion layer with a negative charge on the p side. What is the meaning of depletion layer? Devoid of any free charge carriers, but it will have immobile negative charge carriers available there. Now if you put a AC signal on the metal side, this blue one, which gives you an extra charge of dq bar, then you also get a dq bar on the semiconductor side, and this is given by xd here, and this is xd is that this is basically the width of the depletion, and the increase in the dimension of the depletion region because of the application of a bias is given by this dx. So what we do, it's basically a series addition of oxide charges and depletion charges, and therefore we write 1 by c prime depletion to be equals to 1 by c ox plus 1 by c prime depletion, right. Now therefore my c prime depletion will be given as c ox into c sd prime divided by c ox plus c sd prime. C sd prime is my depletion capacitance. We already know the value of c ox and c sd, right, and we just feed this value into this expression and we get this. So what I get, quite interestingly, is that C prime depletion, the capacitance of my depletion region, is inversely proportional to my xd. xd is the width of the depletion, right. Now you see, very interestingly, this is a value, xd is a parameter which is basically, I told you, as a bias dependent, right, it is bias dependent, correct. So this is bias dependent. Why? Because if you go on increasing the value on the metal side, your semiconductor side will go on also increasing in terms of depletion width. And what happens to my C depletion? The C depletion starts to go down, right, and the depletion capacitance starts to go down. This is for the depletion capacitance here. Let me explain to you therefore from the band diagram here. So in the depletion region, you will have the Fermi level will be something like this. This will be EF, right. And what has happened is that EFI has fallen like this. This is my intrinsic Fermi level, right, and my conduction band has also fallen like this, because this is on the this is on the semiconductor side, and the valence shell will also fall like this, right, they will fall like this. So why? Because you have applied a positive bias, and therefore effectively what you are seeing is that the dipping will take place on the p side. Dipping primarily therefore means that your EFI is coming closer to EF in that sense, right. Now this gives you an idea that there will be a weak depletion region formed somewhere here, right, and this will be immobile charge carriers which will be developed. So this gives you a brief idea about the way you can actually do design for a C depletion. As I told you in the earlier slide, that the total capacitance will actually drop down as the space charge width increases, right? Now let's come to a very important definition from where we will start this lecture's main thrust area, is the concept of threshold inversion point we will discuss here. Let's understand this point very clearly. What happens is, as I discussed with you in the previous slides, that as you go on increasing the positive bias on the metal side, you are attracting more and more electrons towards the free electrons from the substrate or from source drain region on towards the interface side, right, forming a thin layer of depletion region, and we have already studied that point. However, we define and how do you define that you have you have threshold voltage formed, is that when you say that it becomes as much n type as it is initially p type. One way of saying it is that we define the threshold inversion point to be that condition when the maximum depletion width is reached. We have the maximum depletion width is reached, right? And of course, but there is an important here that effectively, but there is a zero inversion charge density, which means that it is slightly different from our previous understanding of threshold. They are slightly different from each other. So we define that condition of threshold inversion point to be the condition where there is a maximum depletion width is reached, but essentially having zero inversion charge. Anything larger than this will extract more and more electrons, minority current carriers near the interface. So we define C min bar to be equals to this, where x dt is basically the maximum depletion width. This is the maximum depletion width of the MOS transistor, correct. So this gives you an idea that the maximum depletion width of a MOS transistor depends on the value of your x dt, right. Now let me explain to you what is an inversion capacitance. Now in an ideal case, if I give a small increment change in the voltage across the MOS capacitor, I am sure I will get a differential change in the inversion layer charge density. The definition of inversion layer was what? That you will have, so let me use the slide to show you. So I have a MOS structure here, right? I have an oxide layer here. This is my oxide layer. I am still using it a 2-terminal device, so let me not go to 3-terminal at this stage. This is my metal and this is my oxide layer and this is my semiconductor. Let us assume this semiconductor to be basically p type, and therefore when you apply a positive bias here, what you are actually doing is your electric fields are all in this direction. So the holes are repelled. When the holes are repelled, you will have a depletion region being formed here. So what it will look like? It will look something like this. Let me redraw it for you. I have a metal, I have an oxide layer, and then I have this semiconductor. Now it will look something like this. Since I haven't applied, this is metal, this is oxide semiconductor. Since I have applied a positive bias here, and let us assume that my substrate is grounded, then there is electric field going from top to bottom, and I am 100% sure that there will be a depletion region which will lie somewhere like this, right. And as you make the voltage more and more positive high, this depletion width thickness will go on increasing. It is exactly like a reverse bias PN junction diode. So I am not going into the diode region, but this is almost like a PN junction diode. And as you can see here, since I haven't applied any bias on the source side or drain side, which we will be doing later on, the thickness of this depletion is basically constant and is equals to x dt. So I have a thickness which is given by x dt, and this is actually dependent inversely on the square root. It is proportional to the inverse square root of Na, doping concentration, Q times Na actually. There are other factors at the top in the numerator, but x dt depends upon inversely. So higher the value of the doping concentration on the p side, right, lower will be your x dt. And the reason is because since your doping concentration is very low on the substrate, your doping concentration is very low. So it primarily means that even if I assume 100% ionization, then if my number of dopant species, let us suppose, is 100, then I will have 100 free holes available here, right? Now in place of 100, if I assume there are 1000 Na atoms, then there will be 1000 holes, assuming again 100% ionization. If the number of holes are larger and larger, then less space or less depletion region will be there, right, for the more and more positive bias, because you don't have to overcome larger number of holes. You have to overcome smaller thin region, more thin region. The thin region will have exactly the same number of holes as earlier, because the charge density is also very large. And that is the reason xdt, which is the maximum depth of the transition region or the depletion region, is inversely proportional to the doping concentration of the acceptor ion, right. At this stage, again I am again assuming for your, I am again assuming this point that these there are no interface trap charges. So there is no interface trap charge here. So what we have done, we have formed this xdt. Please understand, xdt primarily means there is no inversion charge being still there, right. So let us see what we can do here. Since we have understood this basic idea, my C prime inversion, which is the capacitance in the inversion layer, will be again equals to Cox equals to epsilon ox by Tox, right. Very straightforward and simple way of looking, that C prime inverse will be equals to C epsilon ox by Tox. Now you will ask me why we are getting like this, because it is exactly behaving in the same manner as it was doing in the first case when it was in the accumulation region. What was the difference between that inversion layer and the previous layer? If you let me use this depletion capacitance layer. Yes, you see, in the depletion capacitor you initially had the depletion layer, and then when you apply a AC signal, you see the blue region, you have an increase in the value of dq. But in this case at least, you see, you initially have the inversion layer being formed, a basic inversion layer is being formed. So it is almost like a parallel plate capacitor which is being formed in this case, right. And that is the reason we define this to be as epsilon ox by Tox in this case, right. So this is the basic idea of a inversion capacitance. Now let us come to the very important idea of CV characteristics of a MOS capacitor. What do? I take a MOSFET and then I apply input signal, and this input signal varies from few hertz to few kilohertz to few megahertz, right. And then I try to figure out how will the value of capacitance change as you move along. So do not look at the frequency at this stage, just look at C versus V. This is the capacitance on the y axis and you have applied gate voltage on the x axis, right. Now let us start with accumulation region, where your gate voltage somewhere here, your gate voltage is largely negative. So assuming this to be as a p type substrate, my gate voltage is largely negative. When it is largely negative, you very well know it is in the accumulation region. In the accumulation region, the total capacitance is basically equals to oxide capacitance, correct. Now what I do? I go on increasing the value of Vg, the gate voltage. Now as you can see here, it is constant over a period of time, but just as I cross this value, it starts to dip down, which basically meaning it goes down, right. And this goes down primarily because of that C depletion, right. So this is basically the region where you have C depletion, and this C depletion, if you remember correctly, is basically given by this expression here, right. Maybe this expression will help you to do it. It is C depletion is this by this, and therefore as you go on increasing the value of xd, C depletion prime goes on decreasing, and that is what is happening exactly if you see here, right. You see it is falling down, it is going down. I will discuss CFB later on, but it goes down like this. As you go on increasing the value of your voltage, more depletion region is formed, and then you come to a region where your maximum value of depletion thickness is there, or the minimum capacitance is now available. This is the region where you will have xdt as the thickness of the depletion layer. This is the inversion point, and beyond which, if you further increase the value of gate voltage, you enter into moderate inversion followed by a strong inversion. And in the moderate inversion, why the capacitance again rises? Because it tries to reach to a value of Cox, right. If you look as I was discussing with you earlier, if you look back at this expression here, this is Cox CSD prime by Cox plus CSD prime, and the value of C depletion will be less than the least. C depletion prime will be less than the least, and that's the reason what happens in this case when you do a CV characteristics is that you end up having as you move your Vg larger and larger, you end up having the value of the capacitance again rise. Because why it is rising? Because now the inversion layer is getting pulled up. So the minority current carriers from the bottom and from the source drain region are getting pulled up, and the inversion layer is getting formed, and that's the reason your capacitance starts to rise up, because more and more charges are being developed, free charge carriers. Then when your gate voltage reaches to a substantially high value, then you again reach to the original value of Cox, right. So this is a Cox graph for a p-type substrate where the Cox is initially very high, later very high, somewhere in the middle it shows a dip, goes to minimum when you have an inversion threshold, and then again rises to a high value of Cox, right. This is what we say. So it is governed by three graphs here. So I have got C min prime, this is one, this point. Then I have the CSD value which is shown here, this is CSD prime. This is the dotted line is showing approximate value for CSD prime, and then Cox is given by. So it's basically a 3-piece approximation which we are doing. This is one piece, we have a first piece, second piece, and the third piece, right. And this gives you a basic CV characteristics of a MOS device. Now what I do, an interesting small change, and that change is I do this now, that I apply an AC, I have a DC signal applied to a MOS device, then superimposed on that I do an AC signal, and this AC signal varies from hertz to kilohertz to megahertz. So that's the range of signal which you see, right. When we go to megahertz and kilohertz, we define this to be as high frequency, right, and when we go to hertz or below than that, we define this to be as a low frequency, correct. And so with this knowledge which you have gained till now, let us look at the CV characteristics at high frequency and at low frequency. Now what is the meaning of frequency here? You see, the frequency is the input frequency, right, input gate frequency. Very straightforward and very layman language, if you want to understand, you will understand like this, that if your frequency is relatively low, right, input frequency, it primarily means that the charge carriers in the substrate region and in the source drain region get enough amount of time to go towards the silicon dioxide interface if your frequency is relatively low. And that is the reason you see the dotted curve follows exactly the CV curve as we know of it. You see, it goes to the minimum value and then again rises and then fixes up, right. Why? Because in this low frequency, suppose you are giving a signal which is say 5 hertz or 10 hertz, it primarily means that every second there is a 10 times there is a movement of the voltage up and down. In the positive side, the electrons are pushed towards the interface, in the negative cycle they are pushed away from the interface. But since it is very small, the electrons get enough time to move towards the interface, and therefore your CV of low frequency follows the CV of the MOS device as we know of it. But let us look at the point, what happens when we go for high frequency. When we go for high frequency, then we do not allow the electrons to actually in a layman word talk to the signal. So if a signal is varying very fast, the electrons are not able to keep pace with the input signal, and as a result what you will see, the value reaches to C minimum, C min, where at inversion it reaches to C min, right. If you look at the right hand side, the same thing I have shown you here, that I have a positive Q, I have a negative Q here, I have a depletion region, maximum depletion region has been reached, and beyond that I am adding dx value because of this input frequency, right, and that gives you this variation of low frequency and high frequency. So low frequency, the capacitance tends to again move up to its original value. At high frequency, it actually saturates to the C min value as you move ahead in the inversion region, right. And this gives you an idea that if you operate at high and low frequency, what will be the value of capacitances when you apply a specific Vg value in a sense. Let me also explain to you one term which is left was basically the flat band, right? Now let me show the flat band here. The point in the curve is of pretty interest, because the flat band condition occurs between accumulation and depletion, right? And it is given by this. So it is somewhere here. If you see, if you look at this particular point here, this occurs between accumulation here and depletion here. So this is the point when your bands are absolutely flat in dimensions, right? And as a result, so what will happen on the left hand side, when the Vg is very very negative, the bands will be moving up. You start making your Vg higher and higher, the energy band starts to come down. A time one comes when they are absolutely flat, that is defined as my flat band. And then if you go on further increasing the value of gate voltage, it goes down, the energy band diagram goes down, right? So the flat band voltage or the flat band, the capacitance is given by this function. It is given by this function. It depends upon many factors. It depends upon other factors here, and is a function of oxide thickness also, right? So Tox plus as well as the doping of the semiconductor. It's almost the same as your C depletion, right? But has a value which is quite different from C depletion. Let me come to, so till this discussion was without any traps. Now what I do is I introduced knowingly, or even when you do a fabrication, there are always fixed oxide charges available, and as we have seen already that my flat band voltage changes because of this charge. This charge is basically my fixed oxide charge, and phi ms is basically my metal semiconductor work function difference, and Qs is the equivalent fixed charge which is there. We have already seen also the origin of this fixed charge, right? Now what we will do here is that we will take up the flat band voltage shifts. Now let's look at the graph here on the right hand side here. What I do is I go on increasing the value of the charge which is accumulated on the oxide layer. So you see you have QSS3, QSS2, QSS1 and so on and so forth. If you look here, this actually goes on increasing as you move from left to the right, right? So QSS3 has got the maximum charge available. Quite interestingly, you see the flat band point actually starts to shift to the left, which is a lower Vg value as the number of charge carried increases. And that is expected also, because once you have the larger and larger oxide trap charges, right, you require a larger external voltage in order to neutralize it, and therefore the flat band shifts from VFB0 to VFB3 and it goes on increasing. Now since the oxide charge is not a function of the gate voltage, obviously, because oxide charge is a fixed charge which is because of many other reasons, but surely not depending on the gate voltage, the curves actually show a parallel shift. You see, I have shown you a parallel shift here, right? And the shape obviously remains the same. Not only that, the minimum point is also shifting to the left. You see, this was my C minimum, remember? This is my C min 1, C min, this is my C min another, this is my C min again, this is my another C min. So the C min value also starts shifting to the left as you make your QSS larger and larger, right? Now let's look at CV effect with interface trap charges. So now if you have interface trap charges, right, then these interface trap charges lie somewhere in the interface of silicon dioxide, where there are dangling bonds available between. So basically if you look at this point, I have silicon double bond O, double bond O. Now if this double bond breaks down here and you have silicon double bond O and these two bonds are dangling bonds, then what happens is that these form states where the charges can be captured in a very easy sense. You got the point? And therefore you can have acceptor levels and you have donor levels available to you. And these are the allowed electronic states which are there. Is the flat band condition, and I have the conduction band, valence band here, and I have the net charge in this interface, the total charge, the net charge in these interface states is obviously dependent on the function of the Fermi level with respect to these bands, right? Now an acceptor level, you can just note it down somewhere or you can keep it with you in your idea. An acceptor level is considered to be neutral if the Fermi level is below the state, and it becomes negatively charged if the Fermi level is above the state, and vice versa for donor. You got the point? So an acceptor state is neutral if the Fermi level is below. You can understand why, because acceptor states are what? They accept electron, or they will accept electrons, right, making holes somewhere. Now if they are above the Fermi level, primarily mean they will be neutral in nature, whereas in the donor level, when you go below the Fermi level, they will be neutral, and as it goes above Fermi level, it has to have some negative charge. Why? Because it has gone above the Fermi level. So this gives you a brief idea about the CV characteristics with interface trap charges, right, and that gives you a idea here. Look at the last slide here. Therefore if my this is my intrinsic Fermi level, this is my Fermi level. So this is accumulation mode which I am doing. Anything above this will be either neutral acceptors and positive donors. Why positive donors? Because they have donated one electron and they are becoming positive in nature, whereas neutral acceptors, because they have not accepted anything, they are still neutral, they are not ionized at this stage, right. Similarly, if you look at let us say depletion, the next one, you see suddenly it has dipped down, and as a result you will have neutral acceptors above the Fermi level, but you will have neutral donors also below the Fermi level, you see this and this. Whereas if you finally come to the inversion layer, which is this one, inversion here, then if this is my Fermi level, anything below this point are neutral acceptors and neutral donors, and anything above is neutral acceptors, right. So you have negative acceptors here, you will have negative acceptors here, and you will have neutral acceptors here. Why negative acceptors? Because they have now accepted one electron from the side, they have become themselves negative in nature, right, and that is the reason you see a dip here. With this, let me also come to a point where I was just showing to you, then when you have a p type substrate, then the way the CV was working for you was something like this. I will explain to you where the CV was. You see the CV like this, right, it dipped in the positive Vg. So let me draw for you here. So I have this point and then this is there, and let us suppose it comes like this, and then it drops down here and becomes negative, and let us suppose it comes like this, right. However, if you take an n type substrate, right, and I am comparing again with this graph here, I have an accumulation region, I have a Vt min, and then I have low frequency. This is for p type substrate. If you take an n type substrate, it will be something like this. It will come like this, it will dip here, right, and then it will go like this, and then it will come like this. This is for an n type substrate. I will leave as an exercise for you to explain why the graph shifts on the negative side when you do a n type substrate, right. So this should be known to you from the point of view of the CV characteristics of a MOS capacitor. Let me recapitulate what we did till now. We discussed about the flat band, how the flat band shifts with the charge. We also discussed about the interface and oxide trap charges and how they influence the overall capacitance and CV characteristics of a device. We have also looked into the CV interface with interface trap charges. Now what happens in this case is that, as I discussed with you, this is the ideal case, right, and because of the positive fixed charges, they start shifting to the left, and with interface trap charges they shift to the left. You see this curve, if you look, is with interface trap charges, right. Where they cut, the CV characteristics is defined as by mid gap. So when the interface states are present, the amount of and the direction of the shift change as we sweep through the gate voltage, since the amount and the sign of the interface trap charges also change. You got the point? So as you go on shifting the gate voltage, the Fermi level shifts bottom or top, and any acceptor or the donor level state position will change depending on the relative position with respect to Fermi level. So we define this to be as the mid gap, where you will get half the value. This is my flat band voltage which you will get. This is with interface trap, this is without interface trap charges. With interface trap charges, you see, quite interestingly, the graph has actually shifted on the top side to the left and on the bottom side to the right. This primarily means that for the same amount of input gate voltage, you will now have a lesser capacitance, whereas on the positive side you will get a larger capacitance, right, and therefore you need to understand the reason why is it like that, right. You will get assignments on this later on, but you need to understand why we get such type of CV characteristics with interface trap charges. With this, let me recapitulate what we did. We today did a CV characteristics where we tried to find out the capacitance versus voltage characteristics using C depletion, right? We looked into C depletion, we looked into C accumulation, and we also looked into C inversion or C min value here, C min. And we took these three and tried to plot a CV characteristics both for low frequency and for high frequency without trap charges and then with trap charges, right? And we saw that with trap charges, my in the accumulation side my capacitance falls down, and in the inversion side it gets up, right? And the reasons are known to you. I told you to find out the possible reasons for that, right? With this, let me finish this lecture, and thank you very much.